Hello everyone, I'm Lucas Araújo, a PhD student from Federal University of Minas Gerais, and my work is about the study of dose absorbed due to the distribution of gold particles in the culture medium using a voxelized array system. One of the most common techniques used to eradicate cancerous tumors is the use of ionizing radiation therapy. The primary goal is to deliver a uniform maximum dose to the tumor region, rendering it non-replicable. This is accomplished through the direct or indirect effects of radiation therapy, which ultimately leads to cell death. One of the type of the radiation therapy is the brachytherapy, which a radioactive source is placed very close to the area of the tumor or inserted into the tumor. This ensures as uniform a dose as possible. In the case of lung cancer, for example, as you can see, the radiation source is inserted through a catheter into the tumor region to destroy it. For the safety and accuracy of interstitial brachytherapy radiation sources, Task Group 43 of the AAPM provides guidelines, recommendations, and standards. The sources used in this type of brachytherapy are iodine 125, iridium 192, and palladium 103. To optimize the dose enhancement in the target region, high atomic numbers nanoparticles are used to promote local dose enhancement. The goal of these nanoparticles is to penetrate into the cellular region of the target, and by receiving the radiation that normally comes from photon radiation as a primary radiation, these nanoparticles interact with the photons and act as a second radioactive source, generating secondary electrons such as Auger electrons and photoelectrons, thereby depositing doses beyond what was programmed. So the objective of this work is to analyze and simulate the radiosensitivity of gold particles, a high atomic number material, in an in vitro sample using a voxelized array system. It was computed and analyzed the dose response across various proposed geometry models in both homogeneous and heterogeneous mediums. Additionally, we calculated the dose enhancement factor parameters to investigate the concentration dampiness and the energy dampiness with different computational models. To further validate our simulations and compare them with established standards, we simulated the radial dose function outlined in the TG43 guideline for the iridium source utilized in our study. So about the materials and methods utilized in this work, the Monte Carlo code used in this work was the MCNP6 version 2, and the photon and electron library was used, and the particle transport parameters were optimized for the generation of secondary electrons for the photon source. To improve the statistical accuracy of the results, a variance reduction technique was also used. The tally used to produce the results of the code was the tally F6, which calculates the dose deposition in megaelectronvolts per gram on the basis of the electron produced. The simulations achieved a relative error about 1% using 10 to the 9 stories. A brachytherapy setup was created by computational modeling. The model consists of two acrylic plates for the dose homogenization, a high dose rate of iridium 192 source, with the source has 200 43 possible stopping positions, and a 6-well plate representing the real one about this. And the spectrum of the Araújo is notice that the 50% of the emissions probabilities are below energies of 50 electron volts, and with more than 40% of the emissions in the kilo electron volt range, with the emissions probabilities of more than 1%. The sum of these probabilities, emissions, and their respective energies are about 91%, the total spectrum of Araújo. The voxel array system was constructed through the following steps. First, a three-dimensional object was created. This was done using a program designed for creating an object of this type. Specifically, Blender was used for this purpose. Second, the program Binvox read the three-dimensional file and converted it into a three-dimensional binary voxel grid. In other words, the three-dimensional object was converted into a three-dimensional voxel object. In the third step, the Binvox 2MCNP software developed by Professor Telma is used. This software converts the Binvox file into a cell card that can be read by the MCNP code. Prior to this, the voxel object is made of a single material. In other words, it's homogeneous. Finally, the fourth step was performed in which a Python script randomly generated a new material in this voxel array system. In this way, an object originally made of one material is transformed into an object made of two different materials, made randomically. Once the voxel array system had been established, the subsequent resolution and voxels dimensions were determined. This distribution of the voxels will be discussed below. The target was subsequently introduced into the Q3 medium in the 6-well plate. The Q3 medium is a cylinder with a diameter of 3.33 centimeters and a area of 0.01 centimeters or 100 micrometers. So, the distribution of the voxels, of the types of the voxels, is discussed in these cases. The 5 models studied in this work are represented by the examined cases. In case A, the majority of the gold voxels were distributed near the bottom of the Q3 medium and decreased over the 10 voxelized layers randomly in these proportions. Cases B, C, and E were distributed randomly in their respective proportions or concentrations in the Q3 medium. The distribution is in all the Q3 medium in these cases. And finally, case D consists of a homogeneous medium with a gold cylinder that is uniform and homogeneous, placed at the bottom of the Q3 medium. The gold cylinder 8 corresponds with the 8 of the Q3 medium, and all cases have the same 8 and radius. So the dose enhancement factor quantifies the local dose increase due to the presence of gold particles. This ratio is related to the dose with presence of gold particles in medium relation to the dose without presence of gold particles in medium. For example, in the same medium, the presence of gold particles equal to 4 gray, and the dose without the presence of gold particles, in other words, in the water, is 2 gray. In other words, the factor represents double the dose gain in the medium. So, as a TG43 parameter, the radial dose function was represented in this equation. This equation represents the dose ratio of a small water spheres positioned at a fixed angle of p over 2 along the source, as shown in this image. This distance, these positions of these water spheres was simulated from 0.5 to 9 centimeters from the source. So about the results, the initial results compared two types of geometry, heterogeneous and homogeneous, as seen in cases C and D. It's noteworthy that both geometries exhibit similar behavior with regards to dose, with difference ranging from 3 to 10%. The homogeneous medium is distinguishable from the heterogeneous medium based on its location at the bottom of the culture medium, while the heterogeneous medium is dispersed all over the voxelized medium. Two distinct analyses were conducted to calculate dose enhancement factor. The first analysis focused on the concentration of gold particles, while the second analysis centered on energy dependence. Using the distribution of case E, we observed a second-degree polynomial equation in the relationship between depth and gold particle concentration. The equations indicate that the point of intersection, representing a concentration of 0, had a deviation of only 0.4% from the theoretical value of 1, which corresponds to a sample with no gold particles present. Comparing the depth concentration in a published paper using the equation from this study, difference increase as the concentration increase. Maximum difference of up to 5.9% were observed. The dependence of depth parameter or energy was studied in these cases A and B. It's understand the difference obtained while using different low to high monoenergetic sources. The objective of this analysis was to substitute those with energy in order to investigate whether energy dependence exhibits a consistent pattern compared to those. It was anticipated that the dose enhancement factor would converge toward a unity value as the dose increased, regardless of whether gold was present in the study region or not. Regarding the dependence of depth on low energies, it was observed a significant increase in dose enhancement. It looks about these four graphs. This phenomenon can be attributed to the high mass energy absorption coefficient of the material under investigation compared to materials with a higher Z number. At low energies, the photoelectric effect dominates. It's important to emphasize that the analysis is purely computational, originating from particular interaction simulations aimed at understanding depth behavior as a function of energy. Similar results to this analysis can be found in literature. Through the simulations, we attempted to explain the decrease in depth as the dose in the medium increases. Depth behavior in relation to energy revealed that it tends to stabilize at a uniform value as energy in the medium increases. Beyond a certain energy threshold, approximately 0.8 MeV, it looks over here, the influence of energy becomes negligible, whether with or without the presence of gold particles. This suggests that for gold particle treatment, it's advisable to use photon beams with low energy or some brachytherapy sources with intermediate energies. So for energies of 50 to 500 keV, the difference between SDEF for the cases A to B is about to 24 to 5% in respective to this energy. It's observed a decrease of this difference, and this indicates that in experimental setups where the positioning of gold particles is a key factor, maintaining a high depth is of paramount importance. The results of the radial dose function were compared with results published in literature. The largest disparity between the results obtained in this study was 5.7% compared to the values reported by Fonseca et al. And 2% compared to the TG43 report. Notably, significant deviations in the comparative values become noticeable at a distance of 4 cm for the radiation source. Finally, in conclusions, this study provides a comprehensive overview of the modeling and simulations conducted for a brachytherapy setup using a radiation source in vitro sample. Various geometric models were created using voxel arrays, and the results demonstrated the significant influence of geometry on the dose deposited in the simulated cell culture. This in turn has implications for the conclusions drawn for laboratory experiments. These findings enable a more precise analysis of the interaction with cell sizes. The calculation of a radial dose parameter consistent with existing literature is a notable achievement. Moreover, there is a need to calculate additional parameters as outlined by the TG43 guidelines to enhance the characterization of the radiation source for brachytherapy applications. So we thank to the Brazilian institution support for this project and others projects, and find out about our group, the MCMAG, and thank you all, and I hope you enjoy it.